Okay, so we'll do the same differentiation as 2D case. fxy is equal to py. Okay. So if we can bring about fyx, then we're on our way to coming up with a test.
And you could just do that fyx.
Yeah, so we could start with the exact same thing. Okay, so these need to be equal. Now we need to involve z somehow, in a similar way.
Oh, what?
We move on to the next derivative with regards to
Next derivative in what sense?
like fx y z.
Well, we don't want to get a third partial derivative. Second partials is enough. All right, so
you could take the first one, fx, and take the derivative with respect to z.
yeah, okay, so fxz is equal to pz. Yeah? All right, and what can we do with that?
Well,
How can we bring about fzx?
you have the fz over there, and you can take the derivative with it.
Yeah, fzx is equal to rx. So now these need to match. Okay, how do we finish the job?
Do the yz and the zy.
Yes.
Q.
So,
Wow, this is complicated.
so fyz is equal to qz, and fzy is equal to ry. So these two have to match. So these three dimensions, there's three pairs of first partial derivatives of your component functions that have to be equal. So py equals qx. Just like in 2 dimensions. Then we have qz is equal to ry. And we have pz is equal to rx. So now it might be difficult to remember it this way, although we're actually going to, a little bit down the road, describe this test a little differently, because this is equivalent to saying that if you take the vector field f, so pqr, and you take this vector of differentiation operators ddx, dy, ddz, and take the cross product of them, you get 0. Now it's a little odd to take a cross product involving a vector of differentiation operators, but if you were to compute this cross product in the usual way, then you get, and set it result equal to 0, you get exactly these conditions. This is called curl of a vector field F, which we're going to study in the next section. All right, so just a little preview there. So this vector of differentiation operator is something else to get used to, because we're going to take the cross product and dot product of it with vector fields for various purposes. Okay, so however you look at it, at least we have a way of checking whether a given vector field is conservative. So once that happens, fundamental theorem of line integrals. Yeah, we still need to come up with a function little f, whose gradient is big F. Fortunately, there is a systematic procedure for doing it. Okay. Okay. So So I'll show this procedure by stepping through an example. All right. suppose we have this vector field. 3 dimensions. So we have 2xz plus y squared. Then we have 2xy. Then x squared plus 3z squared. All right. So first, let's check. Is it conservative? So we need py equals qx, rx equals pz, and ry is equal to qz. All right. Well, here's let's do p, q, and r. So py is going to be 2y. Qx is going to be 2y, so that works. Rx is going to be 2x. Pz is going to be 2x, so that works. Ry is going to be 0. There's no y in there at all. And qz is equal to 0, so that works. So this vector field is conservative. So big F is a gradient of some function little f. So what is f of x, y, z? Well, for that we're going to use the fact that the gradient of little f is big F. So we know that fx is equal to p, which is 2xy plus y squared. So now what we'll do is we'll undo this. We're going to integrate both sides of this equation. So we're going to anti-differentiate both sides of this with respect to x. So what we'll get is we'll get f of xy, the function we're after. And now we're going to anti-differentiate this with respect to x. So we're going to treat y as a constant. So what is the integral of this with respect to x?
X squared y plus y.
X squared y plus what?
X y squared.
Yes, xy squared. But don't forget the plus a constant bit. That's very important. In fact, it's not a constant because we're integrating with respect to x. So the constant of integration is not really constant at all. It's a function of y and z. All right, so the point is, it's something that's independent of x. So now when you differentiate this, the derivative of this part will be 0. And then you'll differentiate this with respect to x, and you'll get p as expected. So f is only partially specified. We now got to figure out what this function g of yz is. And in order to do that, we're now going to take this, right, this is z. We're going to differentiate this whole thing with respect to y and z and match it to q and r. And that will allow us to figure out what this unknown function g is.
So when we're trying to figure out if it's conservative, should we know that py equals qx and the other ones off the top of one here? Probably.
Yeah.
Okay. I'll add that to my list.
There's always your cross product.
Yeah. But I was thinking about that, but I mean, if you do it so many times,
Yeah.
it's gonna get annoying.
Oh, well, yeah. But if you do it enough times, you'll just know it.
Yeah.
So, well, actually, what I was doing here, you can hear it running it down off the top of my head. So I know that Rx is involved. So as far as what to compare it to, well, X corresponds to P. So P is what's going to go here. And R corresponds to Z. So Z is what you're differentiating with respect to.
Oh, I'm glad you shared that.
Yeah.
I don't have to remember half as much.
Yeah. So, see, because here, P is the X component. Py and Pz are involved. Q is the Y component. Qx and Qz are involved. So you're always differentiating each component with respect to its other variables.